Today is March 15, 23. So what? I corrected the report of the first lab and uploaded it to your group folder. Okay. And just like last semester, you have a folder and a .html file that you must download to see your grade and your mistakes, right? Just like last semester. And if you do not know how to open that file, let me know and I will walk you through during the office hours. Okay. Okay. So regarding the standard deviation, right? No need to put significant figures for the standard deviation there. Everything that's in red. Let me see if I can get the. I'm gonna show you the file, right? Some of the quantities that are in your table, you do not have to have significant digits. Some of them do need to have significant digits. I have corrections, spreadsheets. Okay, let's take a look at this one here. Okay, everything that I put in red do not need significant digits. Okay. See, no significant digits, no significant digits. Okay. So. Okay, good. Okay, and lab attendance. Okay, this lab attendance here. Okay, so we have the correction of the lab report there in your folder, just as a sample. Here is group 7, right? So the correction, to see the correction of your report, you have to download this file and this folder. See? P07L01G07 files. Those two sets of documents, they work in tandem to see the correction. In order to see the correction, you must have those two. If you do not know how to read those documents, just stay around after the class during my office hours. If you do not know how to read those, and if you don't remember how to read those, just stay around after the lab during my office hours that I'll walk you through. Okay, and okay, and today, okay, we're gonna do. Oh, don't forget. Report for lab 2 is due now, right? Make sure you upload that to your group folder. And let's get the syllabus as well. Syllabus today is the, let's see, we did the quiz number 2, right? Last time we did the quiz number 2. Now we should expect another quiz, Let's do another quiz on next Monday. Quiz number 3. Today is lab number 3. This lab number 3, and that's going to be resistance measurements. So you already know, let's just, today is lab 3. It's lab 3, resistance measurements. And how you already know that you can measure voltage with the digital multimeter, DMM. Digital multimeter. But the digital multimeter can measure other things too. But the DMM can measure other things as well. Other parameters as well. That's why it's called multimeter. That is why it is called multi, right? Multimeter. That's why it's called multimeter. Another parameter that the digital multimeter can measure is resistance. Another parameter that it can measure is resistance. The resistances. Okay. And by the way, some DMM can also measure capacitance. It's not all of them that measure capacitance. There are very few out there that can measure capacitance. I haven't noticed that, but it's not most of them. But most of them, let's put a few of them, right? A few DMM can also measure capacitance. We already talked about capacitance. And what else? The quantities that you have in quantities, right? Quantities in E&M, right? Electricity and magnetism. Charge. Okay. There are devices that measure amount of charge, but it's very difficult to be made. This measurement is very difficult to be made. Okay, DMM in general cannot measure charges. Okay, the amount of charge. You need a special device to do that. But what else can it measure? You already know that we can measure voltage, right? Quantities in M that quantities in M that a DMM can measure. Well, take out this charge here. Voltage, definitely. Any DMM that you're going to get out there is going to measure voltage. Okay, what else? Current. DMMs, digital multimeters can measure current as well. Yeah. Anything that you get, any DMM that you're going to get is going to measure current. What else? There is resistance, which is the topic of today. Okay. It does not measure resistivity, okay? DMMs do not measure resistivity. Voltage, current, resistance, capacitance. A few DMM, not everyone, a few DMMs can measure capacitance. And I have my DMM here. I want to check if I'm missing anything. So here's my DMM. I'll stop sharing the screen so you can see the DMM better. And Gotta be right on my face so you can see it. I'm gonna pin my screen here. Yeah, so you can. I'm gonna turn it on. Okay. It's automatic measurement right now, but I don't want to do the automatic measurement. I'm going to select one by one. Okay, this one is voltage. I do not know if you can see the volts, the V there down. DC. It says DC, direct current. And the next one is voltage as well. AC voltage. That AC voltage takes we didn't cover AC voltage yet. This one is resistance. OL means overload. Right now it's measuring a resistance that's very high. Next. Yeah, that's something, that's voltage of a diode. You don't have to worry about that. Ohms again. Yeah, okay, here you go. Hertz, the frequency of a given circuit. It measures frequency. I'm going to write that down to, frequency of an oscillating circuit. An oscillating / AC circuit. Not every multimeter measures frequency either. Let's see if we have one more here. Oh, we don't want that. Let's see one more here. Temperature. This multimeter measures temperature too. Can be used as a thermometer. Many multimeters can be used as a thermometer. But in Fahrenheit and centigrades and Celsius. Fahrenheit and Celsius. And so that's what my multimeter can measure. Okay. Voltage, DC and AC. I didn't see current here in this one. That's so odd. Okay. Let's see. I bought it just recently. Yeah, strange. This one doesn't have current. What a shame. Okay. But most multimeters, they do measure current. Okay. So here you go. Voltage, current, resistance. A few DMM can measure capacitance, and a few DMMs also can measure frequency of an oscillating circuit. Okay, current DC and AC. And what we're going to do today, you're going to work. Today you will work with data, with resistance data. That was collected previously. Just like we did before. And also what we're going to do, we will also measure, we will measure what? We will measure the following. One, the resistance of 6 different resistors. That's 6 different resistors, separate resistors, 6 different separate resistors, and the resistance of resistances connected in series. Okay, that's going to be 5 measurements, and the resistances of resistors connected in series, and the resistance of resistors connected in parallel as well. I'm going to upload those files right now. I'm going to just display one of that. Okay, so here you go. Here's the spreadsheet. 6 resistors separately. And then we're going to get resistor 1 and 2 connecting series. I'm going to connect resistor 1 and 3 in series and measure the resulting resistance. Resistance 1 and 4. Okay. Resistor 1 and 5. And resistor 1 and 6. And that's what this table is all about. Resistors in series. And those are the measurements made by the DMM. And by the way, there are 2 ways of measuring the resistance of a resistor. Either by using the DMM or by using a color code that is imprinted in the resistor. I'm going to show you that. You can go there. I'm going to share the screen, right? Thank you. Here you go. 6 resistors, right? And there are 2 ways of measuring the resistance of the resistor. Either with the DMM, which is the most practical way. Okay. Or by using the color measurement, the color code imprinted in the resistors. That's what they call nominal value. Let's go there in the, and I'm going to write that down too. There are 2 ways to determine the resistance of a resistor. A, by using the color code imprinted on the resistor, on the surface of the resistor. And 2, by using a multimeter. By using a multimeter. It can be either a digital or analog multimeter. You know, the multimeter, the measurement made with a multimeter is far more made with a multimeter is far more convenient. Far more convenient. But you still have to know how to measure, how to use the color code to determine the resistance of a resistor. You still have to know how to do that. You know, at the time, a long time ago, when they start manufacturing resistors, we didn't have multimeters, or the multimeters that we had was very expensive. Okay, so people came up with this color code that we put in the resistors to determine their resistance. Okay. Nowadays, with multimeters that are mass manufactured, and because they are mass manufactured, they're also very inexpensive. You will stop using the color code, but you still have to know, okay? At least you have to know where to look at for the color code. Let's go there. Resistance color code. Right in here. Anywhere you go in the internet, you're gonna find out the color code of the resistance. But let's see. Let's look at the resistors first. You have already seen, okay, pictures of resistors. Okay, here is one. Okay, here's how a resistor may look like. Those things can be very small or can be very large. Okay. Most resistors that we use are going to have only 4 colored bands. Okay. Each of those, the first 2 colors is a significant digit. Is a significant digit of your resistor. Each color code. So each of those first 2 color codes, by the way, first band and second band, they represent digits. In this specific case, the color green represents the digit 5. The color red represents the digit 2. Okay, so those are the 2 significant digits. Now, what about this blue color here? The blue color here is a multiplier. Okay, so here you go. This blue is 1 mega, 1 million. Black is 1, brown is 10 for the third color code. And the last one is just the tolerance of the resistor. Okay, just the tolerance. So this one, which color is this one? I would say this gold. This color here is gold. So if you look here on this table, gold, we have a tolerance of 5%, plus and minus 5%. And what does it mean by tolerance? Okay. I'm gonna walk you through that. Too small. Okay, I'm gonna write that down, the colors. Yeah. How do you read? Here you go. How do you interpret the color code of a resistor? How do you interpret the color code of a resistor, right? Okay, 1. Most resistors have 4 colored bands. Most resistors, notice that, but then there are some resistors that have more colored bands. Okay. The first band represents the first significant digit. Okay. The second band represents the second significant digit. The third band represents a power multiplier, and the fourth band represents the tolerance of the resistance. Although there are resistors with 5 colored bands, the resistor that we use have only 4 colored bands. So you already know that those nominal measurements have only 2 significant digits. Okay, you go, i.e. the resistance has 2 significant digits, Although there are resistors out there with 5 colored bands, with their having a resistance with 3 significant digits. The first band represents the first significant digit, second band the second significant digit, the third band represents a power multiplier. Okay, and the fourth band represents the tolerance of the resistance as provided by the manufacturer. Okay, example. We're gonna get that example that you saw in the type green, red, blue, and gold, right? Resistor with the following colors: green, red, blue, and gold. And you get those colors, you go ahead, go one of those tables, one of those tables that you can easily find in the internet. Okay, and let's go. Green. Green represents number 5. Okay, green, number 5. Red, number 2. Digit 2. Let's put digit 2 instead of number. Digit 5, digit 2. The blue represents what? Blue represents 1 million, 10 to the 6. Okay. The blue, if the blue is in the first or second band, it will represent the number 6. But if it is in the third band, it will represent the number 1 million as a third digit. Multiplying factor. Factor 1 mega. 1 mega. And the gold tolerance, or the tolerance of the gold, 5%. Plus and notice this, plus and minus 5%. Tolerance of plus and minus 5%. Other colors represents other tolerances, like silver, 10%, right? Gold is not used as a color to denote a significant digit, a significant figure. Gold and silver. So let's put those things together. So consequently, for that specific example, the resistance is 2 times 10 to the 6th power with a tolerance of plus and minus 5%. Like that. Okay, and don't forget, all of that is ohms. 56 million ohms. Symbol. 52 million ohms. You know, you can have all sorts of resistance out there. This one is very high. This one is very high. And don't forget, every object has an electric resistance, okay? Every object. Oh. Every object has some resistance. Even my hand has a resistance. Okay. Wood has resistance. Metal has resistance. The difference is that metals are so conductive, so good conductors, that their resistance is very, very low, very small. I can even measure some of those for with my multimeter. I get my probes here. Connect. Turn it on. I'm going to stop sharing the screen so you can see what I'm doing. Okay, auto, let's see, I'm going to put resistance here. There you go. Right now, my multimeter is recording overload because it's measuring the probes of my multimeter is measuring the resistance between those 2 points here that are separated by air. Because air is a very good dielectric, it has a very high resistance. It has a very high resistance. That's why my multimeter is saying overload, OL for overload. Overload means it's above the limit of measurement of this device. If I go ahead and put the probes here in my finger, right? Here you go. black probe on side of the finger, you know, I still get overload. An overload oh, I'm in the way here. Here you go. Yeah, I still get overload because there is, okay, now we start to measure something. Let's see what's this number here. Mega ohm, 7 mega ohm. Okay. But the measurement is not very stable because my hand is not an industrial device, right? Industrial devices, resistances out there, they have pretty stable measurements. And on the top of that, I have blood flowing through my finger, and that may affect the resistance. Now it's increasing. It decreased all the way down to 6.1 mega ohms. Now it's increasing again, 6.7, 6.8, and so on. Okay. If we measure, let's take a look at the metals that I have here. I have this, I'm going to unblur my screen so you can see better. Yeah, better now. It's going to be a little bit challenging to get this thing measured here. Well, one thing that I like to show my students, okay? If I go ahead and touch the metal tip of my probe, okay? Remember, the metal tip, the tip of my probe is a metal. So what does it measure? It measures the resistance of those tips, okay? So you're getting a 0 ohm, okay? Now let's see if I can get this metal here to be a little bit difficult to. Oops. Yeah, I'm getting a very low resistance here. 0.6 ohms. I won't be able to hold the multimeter at the same time that I hold those two probes here in my hand. But it's around 0.3 because it's a metal. Okay, and so on. If we go ahead and measure, I have another metal here. Let's see. This one is a little bit higher, but it's oscillating a lot. 3 all the way up to 10. Let's see. In the side must be. Yeah, it's oscillating. I'm measuring here the nail clipper. It's oscillating. If you want a stable measurement, you just buy a resistor. Those mass manufactured devices that you already saw. Okay, here you go. Another picture of a resistor. And keep the stable around. Okay. And how do you search that in the internet? You're going to search a color code resistor, right? Color code resistor. Color code resistor. And then you have all sorts of tables here in the internet.
Professor, we can see your screen.
Yeah, that's right. Thank you. Let's see. Color code resistor. Go in Google, type color code resistor, and you'll be able to see all sorts of tables with examples of how to measure the resistance. First digit, second digit, multiplier, tolerance. Okay. So, without no further ado, right? Let's start with lab number 3. I will upload your lab report right now, and anything that I have to write it down. Every object has some resistance. Okay. Dielectrics have higher resistances. Resistance to the flow of charge. Okay, don't forget, to the flow of charge. And conductors have lower resistance values. Oh, and what does it, going back to the color code, right? Let's go back to the color code. What does plus and minus 5% means? Going back to the color code. What does the tolerance mean? What does the tolerance mean in the color code? In the color code. Okay, what does it mean? Well, it means the following. It means the following. Okay, it means that the manufacturer of the resistor cannot guarantee an exact value for the resistance value for the resistor, but a range of values. This range of values in the above, the range of values for the above example, the range of values for the above example goes from 0.95 times 10 times 52 times 10 to the 6 times 52 times 10 to the 6 all the way ohms, right? From, okay, which is minus 5% to 1.05 times 52 That's what it means. So you do the math, and that's what the manufacturer can guarantee for you. Okay. If it's gold, it's 5%. If it's other colors, the percentage is different. Like silver is 10%. And the other values, gray, violet, right? You can see, depending on the color, for the tolerance band, you have better or worse tolerances. Okay. And yeah, now let's go get I'm gonna upload your spreadsheets now. Group 1, group 2, group 3, group 4, 5, 6, 7. Right, so we have everybody there. Group 1, okay. Group 1 here. Good. 03, 03. Group 4, 03. It's all there, right? Group 5, 03. Group 6, 03. Group 7, 03. Everything is in there. So you can start working with it. Okay, and measuring. I'm gonna show you measuring. Please download your spreadsheets, and in this meantime, I'm going to call attendance. Eight, Arthur Pacheco, are you there, Arthur? Thank you. Elika Lafay. Elika. I don't see Elika here. Brianna Valencia. Are you there, Brianna? I don't hear from Brianna, but I'm putting a star here. Justena, are you there, Justena? I don't see Justena either. Okay. Ashley Diaz. Ashley Diaz, I don't see Ashley. Natalie Espinosa. Thank you. Jeanette Garcia. Hey, Jeanette, are you there? I see Jeanette in my list, but she's not answering. Randy Bautista. Randy, are you there? Randy is not answering either. Next, Noor Hassan.
Yeah, Professor, I'm here.
Okay. Well, is that Noor?
Yep, that's me.
Thank you. And then Brianna just answered my call. Janet, are you there? Or Randy? Okay, let's move on. Kaylee Hernandez. Kaylee, I can't hear you. And next is going to be Kennedy.
Hello, Professor.
Thank you.
Also, when you uploaded stuff to the Google Drives, my group didn't get the upload, and also it looks like our some separate files were deleted, like our final for lab 2, our submission.
See group number 3.
Yes, sir.
Okay, so let's see here the lab 1 group 3 is here. Okay, and I see everything here, including our lab 3.
Okay, let me just recheck it. Thank you.
Just refresh your screen there and let me know again. I'm going to refresh mine. Yep, it's here, still here. Ryan Ong. Yep, thank you, Ryan. Donia Chapare, right? Donia, I see Donia here. Are you there, Donia? I'm gonna put a star for her here. Vanessa Bonilla. Thank you, Vanessa.
I'm here, Professor. Batista.
Who's that?
Batista. Randy.
Let's see. Randy. Okay.
I'm here too.
Who's that?
Kaylee Hernandez.
Kelly Hernandez. Okay. Blanca Hernandez.
Here.
Thank you, Blanca. Joshua Jimenez.
I'm here.
Thank you. Alondra Lima Abarca.
Present.
Okay, thank you. Daisy Mariscal. Thank you. Yesenia Montes Rodriguez. I don't see a Xenia here. Yeah, no Xenia. And Lady Lud, are you there?
I'm here. I'm here.
Thank you. And we end up having, let's see, 14, 15, 6. Okay, so it looks like, yep, we have the right number. With the exception of those 2 students. Jeanette, are you there, Jeanette? One more chance here. And Donia, are you there? Okay, so let's move forward. I'm going to open my, let me show you also how, allow me to show how we measuring resistors in series. Let's see if you have a good. I want to show you a picture. If they have it here. Taking time. Yeah. Nope, didn't open. This is in parallel. Here's an illustration of 2 resistors in series, right? I want to show you an actual picture. Yeah, it doesn't have a picture here, but we do have. Let's take a look at this guy here.
Okay, so today I'm going to be showing.
Oh, okay. See here, we have a resistors here in this board. Okay, very small, right? Even in my screen here, they look very small. This guy put a bunch of circuits, a bunch of resistors in the circuit. Okay, those 2 resistors are in parallel. He got one lead of the resistor, the other lead of the same resistor. Then you have the lead of this resistor and the other lead of the resistor. So those 2 are connected in parallel. I want to see one that's connected in series. Unfortunately, I don't see it here. Let me get a better video. Series, and maybe this one here is better.
In this video, we have 3 resistors in a circuit. One of the resistors is by itself and will be labeled resistor 1. And the other 2 resistors are in parallel right after the first resistor. These resistors will be labeled as resistor 2 and resistor 3.
I don't like this one either. Let me get another one. I'll have to draw it for you so you can see it better. It's 9:41 right now. Illustration. Field. Let's see. Okay, single resistance measurement. Okay, good. So I will open that file. Resistance measurement. Here you go. Here's a fancy multimeter, okay, different from mine. We have to power this guy up, and then we get our resistor. That's how the resistors look like, right? One lead here, another lead here. I didn't put the color bands. If you want to connect them in series, all you have to do, I'm gonna make it more realistic here. All you have to do is connect one of the sides of the resistor to the other side. In this specific case, I am going to show the connecting, the point of connection right in here. Right in here. They are connected right in here. Move a little bit to the left and this one a little bit to the right. And that's how it looks like those two resistors in series. And then what do? We connect the multimeter to those two ends, okay? Out there, we have this device that we call it a protoboard. Those protoboards are very useful. They sell too, those things, and they are mass manufactured. Another way of connecting those two resistors in series is by what we have here. We have a plastic protoboard with a bunch of holes here in between. Okay, that's exactly how it looks like. And oh, here you go. Here's a protoboard as well. We buy those things out there in any electronic store. Okay, and if you want to connect the resistors in series, you put each lead of them in the same row here that you see, or the same column that you see here. Okay, that's another way of connecting the resistors in series. And if you want to connect them in parallel, what do? You connect the two leads of the resistors side by side, like that. If you want them in series, compare those two, right? If you want them connected in series, just one lead of the resistor is connected to the other. If you want them connected in parallel, two of the leads must be touching the lead of the other one. Okay. And then what do to make the measurement? Okay, you connect the ammeter always in parallel with the resistor. This means the ammeter. If you want to know the resistance of each resistor separately, right? If you want to know the resistance of each resistor separately, what do? Right in here. That's how you connect the ammeter to the resistor. Okay, here's the tip of my ammeter. The tip of my ammeter connected to one, and I'm going to extend a little bit more, okay, so you can have a picture. It doesn't matter where the tip of the ammeter goes, here, but it's important that's on this side, right? If you want to measure the resistance separately, if you want to measure the resistance of the resistor connected in series, what do? Okay, you get those two resistors in series and connect the lead of your ammeter at the end of the two resistors in series. Okay, so let's see. Let me just play a little bit here.
I'll be taking real world measurements using a digital multimeter at the right of the screen. To be honest, I'm making this video because I just got a new breadboard and I wanted to break it in. As per the measurement, there's 5 volts going to the circuit, and the resistors values are 21
here you go.
kiloohms for resistor 1.
See that? He's measuring the
kiloohms for resistor.
He's measuring the resistance. This resistor separately. This one is 4.6, but we do not know exactly what. Let's see.
And 9.8 kiloohms for resistor 1, 4.6 kiloohms for
kiloohms,
resistor 2.
4,600 ohms, because this multimeter is set in the kilo ohm range. Okay, so he's taking the measurement of each resistor separately. Let's start again here.
In this video, we have 3 resistors in a circuit. One of the resistors is by itself and will be labeled resistor 1. Then the other 2 resistors are in parallel right after the first resistor. These resistors will be labeled as resistor 2 and resistor 3. I will be taking real-world measurements using a digital multimeter at the right of the screen. To be honest, I'm making this video because I just got a new breadboard and I wanted to break it in. As per the measurement, there's 5 volts going to the...
Okay, what he did right now, he just measured the voltage in the circuit. That's what he did. Okay, and now he's going to measure the
And
resistance.
the resistors values are 21.8.
Okay, 21.8 for this resistor right here. And 21.8 watts.
Values are 21.8 kilo ohms.
Kilo ohms. Okay, he's using this scale right in here. Okay, he's set up to measure in kilo ohms. The measurement here doesn't show the kilo, right? But because it's too small, in many multimeters it's too small, the kilo symbol. Let's take a look at the other one.
For resistor 1, 4.6 kilo ohms for resistor 2.
Yeah, it doesn't show the kilo here. The kilo is shown here in this scale, but it's very difficult to see it.
And 9.8 kilo ohms for resistor 3.
Okay, now that's how he did it. That's how we do it. We get the resistor itself and just measure them. And
Now, in order to complete this problem, we will have to know how series circuits work and parallel circuits work. You can check out these videos as a refresher. We will start out by finding the resistance total of the total circuit. We can view the circuit.
okay, and we can stop here for those videos. And let's see if we have. Now, what else? Here we go. Yeah, that's all I have here for those drawings, parallel and series, okay, and resistors alone separately. And now what? It's 9:50, right? Let's take our break now. So it's 9:50 right now. Any questions about that? Break from 9:50 to 10:00. Let's go 10:06, right? Because right 9:51. 9:51 a.m. to 10:06 a.m. And I see you in 15 minutes. I'm back here and just reviewing. Remember, what we're going to do in this experiment. What are we going to do in this experiment? Okay, so we'll do the following. 1, we will measure the.
We can't see your screen, Professor.
Oh, you cannot see my screen? Okay. Here. Okay, yeah, got it. What about now? Okay, thank you. We'll measure the resistance of each resistor separately. Okay, and that what table 4.1 is all about. Resistor 1, right? Resistor 2, resistor 3, 4, 5, and 6. That's exactly what you have in there. So the resistor had some color codes in there. The students who got those resistors, they looked in the color code and they wrote that down here. What the value, what's the corresponding value, right? And then what they did next, you know, if it was 5 or 10%, they summed 5 or 10% and display it here. That's the upper value of the nominal value. Okay, we call it the nominal value. The color code, we call it the nominal value. And then they subtract 5% and they got it the lower value. Okay. And you gotta make sure you get all the significant digits right here. Then they got the DMM, digital multimeter, measure the resistance, and recorded here. And don't forget that you have to record you have to display the proper significant figures as well, according to that table that I showed to you, that I gave to you. Okay, so that's the first step in the experiment, in the so-called virtual experiment, where you measure the resistance of each resistor separately, a total of 6. Okay. Then we will connect resistor 1 in series with resistor 2. Then resistor 1 with resistor 3, and so on, right? And so on, for a total. Let's say we will connect resistor in series resistor 2 with resistor 2. Okay. Sorry. Okay, connect the resistor 1 in series resistor 2, then measure their combined resistance. Okay, repeat for resistor 1 with resistor 3, resistor 1 with resistor 4, and so on. Okay. And so on, for a total of 5 measurements. Okay. Okay, that's the next table. Resistor 1, resistor 2, 3, 4, 5, and 6. And the nominal value is already calculated here. Don't forget to display it with proper significant digits, right? And here is the measurement of the DMM. The units go here. Here is the percentage difference between those two values. Notice that the difference is very small, 1%, 1.7, 1.6%. Here's the same thing. The difference is relatively small. Don't forget to put all the units there, right? Oh, what? And then, okay, we are going to repeat, do the same for resistors in parallel. Repeat step 2. Step 2 for resistors in parallel. And that's what this other table is all about. Okay. Nominal value. Nominal value. And what you have here is the inverse of the resistors, right? There's a reason for that. Here's an actual measurement. And what you have here is the inverse of each measurement. Okay, there's a reason for that, right? The inverse of each measurement. Repeat step 2 for resistors in parallel. What else? Okay, on this one here, B, plot. What are you gonna do? Now you're gonna plot it, the data that you got. Plot, let's say this one here. Resistor in series, no resistor. Once you have, you're gonna plot this. Oh, wait a minute. Here you go, resistance values. Okay. Remember, we have very close values between those two. And then what you have to do next? Okay, you have to plot the resistance measured by the DMM against the resistance against the color code resistance. That's your first graph for this first table. Going back. Okay. Plot resistance DMM versus the nominal R sub n. R sub n. Okay, and here you do the same. Plot. If I plot this one, insert, because those values, the nominal value is very close to the DMM value, you should have a straight line with a slope very close to 1. Here in this case, you know what happened here in this case? In this case, we got a resistor that was very high. Okay, this one was 8,000, more or less 8,000, and the other ones are very small, between 60 to 300. Because of that, you have a bunch of points right here at the beginning of the graph, and just one lonely point in there. Okay. In this case, you know, most likely you don't have it there in your own plot. And then you got a trend line. Yeah, here you go. Format trend line supposed to be a linear graph because there is a relationship between the measurement of the DMM, and the measurement using the color code. I'm going to display equation on chart. Man, it seems so small, right? Here you go. I'm going to display this equation on chart. Man, yeah, better now. For some reason, those fonts here are very small. Small. Okay. And the R square shouldn't be 1. Okay, it should be different than that. Let's see if I can get format, select data, font. I'll have to do the format, send line label. Time number. I have to put more decimal places there. 5, 8, 1, 3. Yeah, okay. So that number is so close to 1 that I have to put all those decimal places there for the R squared. See that? If I put only 7 decimal places, it becomes 1, right? That's the advantage of performing experiments with electrical devices like this one. We get R squared that are very close to 1. Look at the slope here. The slope is supposed to be 1 for an ideal experiment, but it's a little bit off. It's off by 2%, less than 2%, 0.9828. And we have this small, intercept. right in here. Okay, so that's my first graph. Single resistor, it will display all the message here. Here in this case, you have 6 points for the first one. What about the second one? Okay, the second one, you do the same. Nominal value. Here in the case of nominal value, what are we doing? We're just summing up one resistance with the other, right? Resistance 2 with resistance 1. You gotta get the right significant digits here, the right significant digits here. Don't need to write down the significant digits here because this one is in red. Okay. Now and we're gonna plot this one as well. Chart. Okay, that's what I'm getting here. It still looks like a straight line. Let's see. Font. I want a larger font here because it's so small. Format. Let's see. Font. Is it the one? Yeah. Okay. Let's increase here to 14 so you can see better. 14 seems a little bit smaller too. Don't forget to put the labels of the graph. 14 as well. Okay. And trend line, display equation chart, and I gotta increase the font size here as well. So you can see it better. Let's put 18. Okay. Now, just like before, we get a R squared that's very close to 1. The slope is close to 1 as well. What does it show you? What does it tell us? Okay, it tells us that the resistances of the equivalent resistance of resistors in series, they do add up. Okay, and that was exactly what I did here. Here, what you see right in here is your experimental value. Experimental, no, just the theoretical value, because I summed up the resistance here. Whereas in this column here is an actual experimental value. Experimental value, theoretical value. Okay, so the theory works very well. Not only the theory works very well, but the nominal value of the resistances is very close to the measured value of the resistance. And then we have and the last one. What we're going to do? We're going to do the same thing, but instead of plotting this one here, we're going to plot this one here, right? Do you remember that the equivalent resistance of resistors in parallel? What do we have? We have the inverse of the resistance is equal to the sum of the resistors, right? Of the inverse of the resistance. That's what I have here. You know, inverse of resistance, resistor number 1. Here we have inverse of resistance number 2, 3, 4, 5, and 6. Resistor 1, 1, 1, 1, 1. And we are getting resistance 1 and 2 in series, 1 and 3 in series, and so on. Then we sum them, that's the summation, according to what we covered in class, right? And we plot that against this inverse. Here's my measurement, here's my result. insert it. Okay, and just like before, we get some points a little bit off, right? Not evenly distributed, and let's put the red line here. And I have to increase again. Yeah, okay, there's no need to increase. Now you can see better, right? Let me see. Yeah, I do need to increase. 14, 18, let's put 18. Yeah, this one I put 16. Font. Okay, now I can zoom out. Again, this loop is very close to 1. This R square should be different of 1. Make sure you get the proper decimal places there, okay? Format line label. When I go to numbers, how many decimal places do I need? Yeah, it looks like I need 5, maybe 6. Okay, yeah. 6 decimal places. Those are the graphs that I got for those. You should do that too. Let's go one by one. One by one here in my roster. Okay, Artur, this. Yeah, Artur Pacheco, did you download the spreadsheet? Yes. Okay, good. So I'm gonna put it here. So the first thing you gotta do is plot graph 1. Did you plot graph 1? Let's put yes, right? Yes. Okay, good. So you got plot graph 2 and 3 as well, right? That's your priority right now. Elika, are you there? Doesn't look like she's here. No, I don't see Elika here. I'm gonna put O. Brianna Valencia, are you there? Okay, you did both. Okay, so you did download it and you plot graph 1, you plot graph 2 and 3 as well. Oh, already. Okay. Graph 2 and 3. Okay, so let me. What about you, Artur Pacheco? Did you plot graph 2 and 3 as well? Hello, Artur. Yeah, both of them. Okay. Okay, so we start working on the units, right? This one here, Justena, are you there, Justena? Hello, Justena, I can't hear. I don't hear from you. Okay, I'm going to skip Justena for now. Ashley, is Ashley here? I don't see Ashley. Justena, I see her here. I'm going to put a star in her name for now. Oh, okay, good. So you're here. Did you download the spreadsheet? Working on it? Okay, working. I'm gonna put that here. Good. Next is Natalie. Natalie Espinosa. Did you download the spreadsheet, Natalie? Yes. Did you plot the first graph? Yes. Second, first, second, and third graphs. All 3. Okay. So start working on the. I'm here. I download the spreadsheet and I have the graphs. Okay. Good. So here go Jeanette. Okay, I downloaded it and I have all the 3 graphs. Good. So start working on the units. Please, once you have finished the graphs, right? Start working on the units. Randy Bautista. Are you there, Randy? I don't hear from you, Randy.
He had to step away for a second, but he was working on it. I think he finished.
Okay. So okay, okay. I need him to get back to me. Okay. So let's see, Noor. Are you there? Is Noor there?
I know that she was working on it as well, and Kaylee. We were because we're in our group talking about the graph.
Okay, that's. Let me see. I'm a little bit confused here. Is that Noor who answered me or someone else? Okay, I'm gonna put a star here. Okay, for now. Until I hear from them. You go, Kaylee.
Yeah.
Okay, good. Kaylee. Okay. And so did you plot graph 1, 2, and 3?
Yeah.
Okay, good. Okay, and okay, Randy and Noor is in group 3. Okay, good. Now I understand. Okay, so here you go. Kennedy, did you?
Yes, sir.
Group 1, 2, and 3? Group graph 1, 2, and 3?
Yes, sir.
Okay, good. So I start working on the units, right?
Okay. Thank you.
Welcome. Ryan Onk. You there, Ryan?
Yeah, I downloaded it and I have all the 3 graphs.
Okay, good. So I need you to start working on the units, please. And Donia, are you there?
Hi, yes, I downloaded it and I did the 3 graphs.
Okay, good. So work on the units, please. Vanessa Bonilla. Vanessa, I see Vanessa here. Okay, I downloaded plotted graph. Okay, that's good. 1, 2, and 3. Blanca Hernandez.
Yes, for all of them.
Oh, then, okay. And Joshua Jimenez.
Yes, got all of them plotted already.
All the 3 already?
Yes.
Okay, good. And Alondra. Okay, you have them out. Good. Start working on the units now. Daisy. All 3. Okay. Yesenia. Is Yesenia there? Yesenia is not here. And Leiblut.
I uploaded to graph and I download the Excel.
All the 3?
Yes.
Oh,
Yes, I finished the upload also.
okay. So plot G1 and then we need, okay, now units, right? Units, fig. Okay, I'm going to close those 1, 2, and 3. And 30. Okay, there is nothing. I got it, and we're having, okay, but we're good now. Okay, good, thank you. Randy, right? 1, 2, and 3, 4, here you go. Okay, and Kyla. Okay, good. So, Pacheco, do you manage to do the units? Arthur Pacheco. Yeah, good. And units. Sig fig. Oh, I already did that. Okay. Sig figs and CL. CL, right? Next is going to be Brianna. Did you manage to work on the units? I'm working on that. That's good. Justena. Let's go back to Justena, right? Yes, you got it. You got, let's see, you downloaded. Did you plot graph 1, 2, and 3? Okay, what about the units? Did you manage to do the units as well? Work on that. Okay, good. Now, Natalie. Did you finish the units, Natalie? Yes, what about the sig figs? Also good, and now the CL, you gotta work on the CL, right? Did you finish the CL already, too? Still working, okay, good to know. Next is gonna be Jeanette. Do you do the units, Jeanette? She working, good to know, okay. And Randy, how are your units doing there? Good. You finished the units. You finished the units of your. Yes. Okay. Good. What about the sig figs? What about your sig figs? Almost okay. I'll put it working here. Next is Nur, right? Download the lab. Okay. And okay, I already marked it here, Nur. And what about? Did you do the graphs? I guess you did the graphs, right? And the units as well. Okay. What about the sig figs? Working. Okay, good to know. Kaylee,
Yes,
both the units and the sig figs?
I'm still working on that one.
Okay, good. Good to know. Kennedy?
Yep.
Yep, for both?
Yep.
Okay, then what about the CL? Are you doing? Are you working on that now?
Yep. All
Very
good.
Good working here. Ryan Ong. Hello, Ryan. I cannot hear you. Oh, here you go. Working on it. Okay, you are working on the units, I presume, right? You got the CL, but what about the units? Okay, so you're working on the units and the sig figs. Okay, you didn't get there yet, right? Okay, I'll leave like that. Next is Donia
I'm still working on it.
in the units. I put here, you're working on the units. And Vanessa, how are you doing there, Vanessa? I did the unit and SIG, but work on the CL. Thank you. Blanca Hernandez. Blanca Hernandez, I cannot hear you, Blanca. Okay, I'm gonna put a star here in Blanca. And Joshua Jimenez.
Yeah, finishing up the units. I'm about to start on the CL right now.
Okay, so you're starting the CL.
Yes.
What about the sig figs?
Yeah, I finished the sig figs already.
Ah, finished the sig figs. Okay, and working. So you finished units and sig figs. Good, thank you. And Alondra. Working on the units, Alondra? Yeah, okay, good, thank you. Daisy, Esmeralda Mariscal. Working, okay, I'm gonna put working on the units. Yesenia. Yesenia is not here. And Lebilud.
I am working on the units right now.
On the units right now. Okay, thank you. Okay, any questions? While you work on that, okay. I just want to share something that I discovered just recently, you know? You're not gonna believe it. I should have known that thing long time ago. You know, I didn't know about that. I discovered like 2-3 weeks ago, I discovered that there is something called this UPS device, an interruptible power supply system. Okay, it's a device that you connect you connect your computer and your mode to. And this device has a battery there inside. When the power goes down, you know, this UPS system kicks in and feeds electricity to your computer and your modem, and you don't you keep on working even in a power outage, okay? But you keep on working up to a certain point. I didn't know about that stuff, you know. So just surprising for me, and now looking back, it's so obvious to me that something like that existed. You know, how come I didn't find that out before, right? So just pointing that out, right? Because when we are working here online, every now and then there is a power outage, right? Either here in my place, it has happened last semester, right? I get a power outage here in my house, or there even wherever you are working there in your home or in your workplace, wherever you are, right? So if you have a device like that, no, it can provide you power and make you and allows you to continue working while the power is off. There are all sorts of UPS devices, you know. This one, like, oh, this one is in Brazilian reais, not dollars. Let's see if you have any dollars here, but that's the price range. Brazilian reais 359. It's something like $70, $70, $80. This one should be $700. No, this one is more expensive because it allows you to stay because it has more power than the other ones. Okay, let's say if this one allows you to stay in for 1 hour, if it has enough power for 1 hour, this one will have enough power for, let's say, 10 hours, right? 10 times the price. Just you know, a little piece of information that I discovered, that there are some neat gadgets out there, right? And there are so many gadgets that sometimes we do not know that they exist, because just the array of devices, that gadgets that exist out there, and you know, happens to be very useful. Okay, if you want to take a look at that, uninterruptible power supply, Wikipedia has an article about that. Okay, so here you go. You can connect, for instance, your computer to this port. You can connect your modem to this port, and even your screen to this other port, right? 3 exits. 3 inputs, but you can increase the number of inputs just by adding an extension, right? Although the UPS device has 3 inputs here, if you get an extension with additional inputs, you can connect even more devices. Just be careful not connect too many devices, because this thing here has a power input limit. Okay, and here you go, uninterruptible power supply, or uninterruptible power source is an electrical apparatus that provides emergency power to a load when the input power source or main power fails. Okay, and they have those things in all sorts of places, especially with people who deals with computers that they cannot have their computers down for too long. So they install those things to keep them going for some time and save the data. Okay, the world's largest UPS 46 megawatt battery energy storage system. Okay, the one that I have is not megawatts. The one that I have is kilowatts. Megawatts is 1,000 times more powerful. But we have consumer devices that are smaller, and that you won't need a megawatt type of storage system. It's too much for us and too expensive too. So all you need is gonna be like a kilowatt, okay, device. And if you want to, here you go, here the diagram, the circuit diagram for something like that. Something nice to have in mind, so you can keep on working in case the power goes down. Uninterruptible power supply, and what I want to show you is some simulations. Colorado physics, Colorado. This is Colorado State University. Must be this one here. There is FAT. Here you go. FAT simulations. If I encourage you folks to go to this website, because it has all sorts of simulations in physics that allows you to visualize many of the concepts, many of the ideas that I'm covering here. Okay, and they have not just physics, but they have chemistry, math, earth science, biology, and so on, right? But we're interested here in the physics. I'm gonna give you, let me go to this one here. And I'll give you the link. Here you go. Yeah. Okay, so I'll give you this link. FAT simulations, right? To everyone in the meeting. Okay, so what we are seeing right now is electricity, magnets, and circuits. That's what we're seeing right now. Okay, and what I like the most here are the circuits. Here's the capacitor. Here's the Coulomb's law. Okay, that shows what. See, we can run this guy. We cannot run that. Let's see, simple learning goals. Let's try this. Yeah, for some reason I cannot run this teaching resource activity, translation credits. Learning goals, charges and fields. Must be this one. No. Charges, let's see this one. Looks like they changed the website. Okay, so here you go. Yeah, here's the electric field of a point charge. Okay. Direction, okay. And then if we add another charge, the field of the negative charge interacts with the field of the positive charge and disturb it somewhat, right? That's one. And electric field hockey. Let's see if this one works. Yeah, this one works. No, they changed the website here slightly. Okay, good. Now we have it. And here are the forces, right? Those are Coulomb's law. We can change the electric charge value. I'm decreasing the electric charge value, consequently the force decreases. I increase the electric charge value, consequently the force increases. Okay, and can I change the distance? Oh, I can change the distance too, right? So the force decreases. I want to see if I can find for circuits, since we're working with circuits here. Motion, electricity. Yeah, it's only physics. Okay, and I want only electricity. Let's see if it's true. Okay, you have all those simulations on electricity here. Okay, and the one I want to show you is, let's try this one. Let's see. FET. Okay, here you go. We have it. So what we're doing today, what are we doing today? Yeah, we're measuring the resistance of different resistors. Okay, so we go ahead. Just a very nice way to illustrate, right? Here's the case of a resistor. I'm going to connect a wire to this resistor. One lead, the other leads of the wire. Okay, look at the bands of your resistor, brown, black, black, right? Brown, black, black is 10 ohms. Brown is 1, 0, black is 0, 1 and 0 is 10. Black is also 0, so 10 to the 0 is 1. So it's 10 ohms. And the gold is the 5% tolerance, okay? And now they came up with the voltmeter here. They don't have ammeter. I don't see ammeter here, unfortunately. Yeah, but you can measure the voltage. Here you go. See, here's the probe, right? Of my voltage device, my voltmeter. Because there is no power applied to this resistor, the voltage is 0. But if we want to add a battery, we have a battery here. Okay, we can add the battery to my circuit. Here you go, 1. Here you go. And now we have electric charge flowing through this circuit. I'm going, yeah, let's disconnect it. I want to make it, this circuit looks better. Okay, and okay, 9 volts. And here is how you should visualize the current flowing through the circuit. If it's electrons, the electrons goes from the positive to the negative in the battery, right? But if you just illustrate the conventional direction of the current, the conventional direction of the current is the direction of flow of the positive charges. You end up having this flow for the current. Okay. Let's see. You can also measure the current with an ammeter. It's written ammeter here. Let's see if they have wire resistivity. No. Yeah, unfortunately, they don't have the multimeter here for us to measure the resistance of the device. But to measure the resistance of the device, what you have to do? You have to break the circuit, the resistor from the battery, okay? And the ammeter would be displaying the resistance of the resistor here. Unfortunately, they don't have that here. They have only the voltmeter and the ammeter. So that's how your resistors look like. Let's take a look at others that we have here. And there are more, okay? They have a simulation of the capacitor as well. We go capacitor. Here's the capacitor. No, I don't know. That's not a simulation. Okay, here you go. Here's the capacitor. Okay, right now we have this capacitor that has a given capacitance. And we can connect it. That's going to be our next class meeting, next lecture. We can connect our capacitor to a resistor. Okay, now, and then what else we need? We're going to need a battery. We didn't study that yet, but we're going to see it very soon. That's what we call RC circuit. Okay, now look what happens in this type of circuit, right? I will have to tab circuit element added. Unfortunately, this capacitor, what happened to this capacitor? He charged it rather quickly. And I am going to discharge this capacitor. Let's see if it's gonna accept it. How do I discharge the capacitor, right? I get a wire. And if I'm doing everything right, connect. Yeah, I'm discharging the capacitor. The capacitor became discharged. And I'm going to do something else. So what I did here was to put the capacitor, to short the capacitor, do a short circuit here to the capacitor. And now the capacitor is back charged. Okay, it's charged back. I'm going to do something else. I'm going to put a switch in my circuit. Oh, here you go. Here's the switch. Switch is nothing but a wire that you connect and disconnect. Okay, now I'm going to break this connection here. I don't need it anymore. I'll put it in the trash can. Oh, he didn't. Okay, good. One more. Yeah, trash it. Good. And now I will connect this guy. But first, I want to discharge my capacitor. Okay. I didn't discharge it yet. Right now, the capacitor is charged. You can see the charges here, negative and positive. I'm gonna close the circuit. Yeah, you see that the capacitor being slowly discharged. Okay, that's exactly what happens in real life. And I can even increase the resistance of this resistor to make sure things go more slowly. And I'm going to go back and charge my capacitor again. I'm gonna open my switch. Right now I have a larger resistor here, 120 ohms. Okay, I'm gonna connect my battery. My capacitor is still discharged. And I'm gonna close. And now the capacitor is charging more slowly than before because the resistance of my resistor increased. The period of charging of a capacitor increases with the resistance. We'll be covering that in the lecture next time. RC, that's what we call an RC circuit. RC for R for resistance, C for capacitance. Okay, and then I can discharge this circuit again. I will cut loose my battery, and the moment I connect this wire, while the capacitor, while those two wires are disconnected, the capacitor holds its charge because the charge has nowhere to go. The charge cannot jump from one plate to the other. The charge cannot jump between those two ends of the wire. But once those two wires are connected, look what happens. The capacitor slowly becomes discharged. Okay, it's taking longer because the resistor is higher. I want you to press a little bit this with this simulation so you can have a good picture of how circuits work. Okay. And we can even connect my multimeter here to this capacitor to see its voltage decreasing, right? Or increasing. Yeah, we have 0.26 volts right now, and the voltage is decreasing. The voltage is decreasing because the amount of charge is decreasing as well. What's the capacitance of this capacitor? Oh, here you go. The capacitance of this capacitor is very high. It's 0.1 Faraday. Okay. There's another type of circuit that we have out there, and still discharging, but it's discharging very slowly. See, 0.15, 14, 13, 12, 11. Eventually, it's gonna come to 0. Right. So let's. I want to. Should be 11:03 right now. Let's have our break, and then we continue those simulations here. It's a very useful tool, this one that you see right in here. If you're seeing circuits for the first time, it's a very useful way to visualize what happens in a circuit. Okay. 703. And any questions before we go to our break? We're going to play a little bit more when we are back. We're going to play a little bit more with this simulator. And two for resistors in parallel. Okay, now it's 11:05. If you do not have any questions, let's have our break until 11:20. Break from 11:05 to 11:20 a.m. Okay, and I see you in 15 minutes. I am back here. Any questions whatsoever about the experiment? That's rather straightforward, right? So, you know, I'm going to write down here in my notes. Take a look at the simulations, at the FAT simulations, right? FAT simulations that are in the following website. This one here. Pay special attention to the circuits simulations. And let's go back here. This one, let me get out of this one here. Okay, so this one for circuit construction, you can build any circuit with this simulation here. This one is for circuits specifically, right? If you get lost, you can go into this website, the simulation for circuits. The simulation. Oh, I have to share the screen, right? Here you go. Okay, so here you go. Take a look at the FAT simulations that are in the following website. Pay special attention to the circuit simulations in the following address. Here you go. This one here. And now you can start building circuits with the simulator, okay? So, you know, starting from 0. Every time that you have a circuit, you will always use wires like this one here. When I use a resistor, okay? And don't forget, you can vary the resistance of this resistor anywhere between 0 ohms, right, all the way up to 120. It doesn't go higher than 120. This is a very simple simulation, okay? There are far more involved simulations out there. They even sell those things out there. But it's far more powerful than what you see right here. I like this one because it's very simple, very easy to learn. Okay, I never managed to learn the more involved ones. It requires too much, and here you go. We have the wires. I can put my switch right in here to allow the current to control the flow of the current. And I'm going to connect a battery to the circuit. A battery, here you go. And then I'm gonna close my circuit with these wires. Copper wire, resistor. There you go. Okay. Right now, there is no flow of electric charges whatsoever. And in this simulation, you are seeing just the flow of electrons because I clicked the electrons here. I'm going to unclick it so you don't see any flow of current, current whatsoever. Okay. So here is going to be the positive side of the battery. Here's the negative side of the battery. I'm going to show the current again, but instead of displaying the flow of electrons, I'm going to display the flow of the current itself. And in order to do that, now I have to have my circuit to be turned on. What I'm going to do, I'm going to close my switch. Here you go. And that's the flow of the current from negative to positive. And look at the pace of the current, right? It's moving very slowly. Why is that? It's moving very slowly because we're using a very high resistance. The flow of charges is very weak. If I decrease the resistance of the resistor from 120 to 10, for instance, okay? Here you go. Look at the flow of the current, how it increases. The electrons start to move faster because the resistance changed, right? Right now I have 6 ohms here. That's what you have to visualize in this type of circuits. You have a resistance. That's the simple circuit that you're going to see out there. Okay, so look at the first, first work on your own, right? Simulation that has a resistor, a battery, and a switch. Okay. The switch is just like the switch that we have there in your house that you turn on and off the light, right? So that's what we are doing here. We're turning on and off the light. Now, right now, in this case, turning on and off the current, right? If you have a light bulb here at this point, the bulb is gonna turn on. I'm gonna open the circuit now, okay? Let's take this resistor from here and put a light bulb. Here you go, light bulb. Here you go, light bulb. See at the tip below, right? Let me cut this one here. Let's see if I can make it look nicer. Huh, strange. Ah, okay, good. Ooh. Okay, I'm going to do like that to make it look nicer. I'm going to line up and just want to make it look nicer. Here you go. Now you have a light bulb. That's how light bulbs connect to circuits, okay? One wire goes to the tip. The other wire goes to the side of the flashlight, of the lamp. What this black band that you see here, what's this black band? Is a dielectric device. So you don't short circuit the lamp, don't short circuit the circuit. Okay? So we have a physical separation between this metal that's here at the tip of the light bulb and this other piece of metal that's here. Between those two pieces of metal, we have a dielectric material to isolate those two. Okay? And the filament that you see here is just a continuation of your circuit. Your wire enters the tip of the light bulb. Inside the light bulb, you have this filament that goes around it and then exits this way. Okay, and then we have a closed circuit. Oh, it's still open, right? It's not closed yet because my switch is open. But when I close the circuit, look here. That's what happens to the flow of current. And I can control, I'm going to open it here, right? Close it, right? At this moment, the light is very bright, but I can control the brightness of the light by putting a resistor here in this circuit. Here you go. And not only I'm going to put a resistor here in this circuit, but I'm going to control, okay, the resistance of the resistor. Okay, so I'm going to close it, right? And watch for the rays here of the light bulb, right? Where we have a very low resistance. I'm going to decrease it. Oh, do you see how the light rays of the bulb increase and decrease, right? Right now I have 0 ohms. But as I increase the resistance, the current decreases and the light bulb becomes weaker. Okay? There are circuits that at home that works just like that. We call it potentiometers. Those are knobs that turn on, you know, clockwise and counterclockwise. Okay, we have those things that at home. Okay, and now the current flow is very small, right? That's one way they can do, one way to play a little bit with that. I'm going to take it out this thing here. Yeah. And I'm going to connect my resistor back here. Okay. What else am I going to do? Okay, I'm going to get this voltmeter and connect here to measure the voltage. It's 9 volts. Why is that 9 volts? Because my battery is a 9-volt device as well. Okay. Oops, it's not measuring. Why is that? Okay, good. We got it. It doesn't matter where I put this probe. I can put this probe here, or I can put it here. It's still 9 volts. Here is 9 volts. Here is 9 volts, right? Here is 9 volts. Here is still 9 volts. But if we go across the resistor, what happens to the reading? It becomes 0 volts. Here is 0 volts. Here is 0 volts. Why is that? Because we have a conductor from here to here. A conductor with 0 resistance from 0 to here. Okay. What about my resistor? It's still going to be 9 volts. I'm going to put a resistor in series with this device. And then I'm going to measure the resistance as well. Okay, so here we go. Okay, now, you know, what happens to the voltage here? Became 7.57, see that? It's no longer 9 volts. It's going to be 9 volts if I connect it here, right? Make sense? And then I can vary this voltage by adjusting this resistance as well. If this resistance goes to 0, you should have a 9-volt measurement across the polarities of this, across the ends of this resistor. If my resistor that increases further, then we have a lower voltage here, a lower drop of voltage here, 2.76, right? Anywhere in between, you know, it's going to be, let's say, 4. If I get it 4.5, exactly 4.5, what does it mean? Okay, it means that this resistor here is exactly equal to this one. See, green, yellow, black, and gold. Green, yeah, orange, right? Black and gold. They're exactly the same value. 53 ohms, 53 ohms. Okay, 4.5. So play a little bit with this device, okay, and you can do the same for resistors in parallel. I'm gonna get this guy out of here. Yeah, here you go. Let us get those in parallel now, those resistors in parallel now. I'm gonna open my switch. And I'm gonna get this guy here connected here. Open it. And I'm going to connect those two resistors in parallel. Okay, those are in parallel now. I'm gonna change the resistance value here so I don't have exactly the same resistance. Right now, the circuit is open. Consequently, the voltage drop here is going to be 0. Okay, here is 0 because the switch is open. But what if we put here between the ends of the battery, right? Now it's 9 volts. That's because this circuit here is open. Let's put it back here. And then when I close the switch, we have a measurement of 9 volts between those two ends. And look what's happening to the current. The current leaves this device, right? Current I, it splits through this branch and go to the other one. Just like cars in at the junction of a freeway. Oh, I'm failing to record that. Well, it's recording. Oh, it's recording, right? Okay, good. Or being recorded here. And you can even measure the current through this circuit. We have a ammeter here. It's not a multimeter, right? It's just a voltmeter, an ammeter. Unfortunately, they don't have an ohm meter. Unfortunately, we cannot measure resistances here. I will open the circuit. And now I'm gonna get my ammeter inserted here. Let's take this one out. I'm gonna get my ammeter inserted here. Okay, here you go. Now I inserted my ammeter here. The current is 0. Even better, I'm not gonna put it here because it's vertical. There's a better place to put it. I'm gonna put it here. So you stay in the horizontal. And whether I put my ammeter here or there is still gonna give me the same measurement. Oops. Here you go. Oh. Yo. Good. Let's see if I get it. Oops. Yeah. Oh. Thing doesn't get that. Ah, man, that's gonna be very difficult. Okay, let's leave this way. You see it? We have a current of 0.28 amperes here. Okay. And very important, you know, those two devices works very differently. The voltmeter, how do they work? The voltmeter is always connected in parallel. By the way, this is part of the lecture, okay? Part of the what is taught in the book, okay? The voltmeter is always connected in parallel. The voltmeter is always measuring the difference of energy, the difference of potential energy between 2 points in the circuit. It works just like in physics 37, right? We measure, we obtain the potential energy of a mass, and this potential energy is not a potential energy, but it's a potential energy difference. It's a potential energy difference between 2 points, right? Between, for instance, the ground, where we set the potential energy equal to 0, and some other place where I set the potential energy greater than 0, if it's above it, or negative, it's below it, below the ground. It's the same thing here. You have a potential energy here, and you have another potential energy here. And then we have this difference in potential energy between those 2 points. But what this device displays, not the potential energy, it displays the potential, the electric potential, the voltage, 9 volts. Okay, and what's a very important difference between the voltmeter and the current? The voltmeter, you connect it in parallel. The ammeter, you always connect it in series. Very important. Okay, this is part of what's taught there in the and I'm going to write that. That's taught there in the book. I'm going to write that for you. Okay. We using the above link, right? We can build different circuits. We can not build, simulate. We can simulate different circuits. We can simulate different circuits, measure the voltage with a voltmeter, and measure the current through the circuit with an ammeter. Okay. One very important piece of knowledge. Okay. One, the voltmeter, you always connect it in parallel with an element of the circuit. The voltmeter was built to be connected in parallel with an element of a circuit. Two, the ammeter, the device that measures current, the device that measures current, is always connected in series with an element of a circuit. You cannot connect it in parallel. Otherwise, you can damage the ammeter. We can do, and the voltmeter too. You cannot connect it in series. Otherwise, you're not going to get a proper measurement. Let's see what happens when we do that. That's how you're supposed to connect those devices. Okay. Now, suppose that I make a mistake, and people usually make mistakes when they are playing with those circuits for the first time. Suppose I decide to connect my voltmeter in series, right? Between those 2 points. See? There's no element in there. Okay? It is when I connect this probe right in here, it is as though as I am connecting it in series with the circuit. Okay, so here you go. the current, the supposed current goes through here, pass through this black probe, and go to the other one, right? That's this voltmeter is connected in series right now. Let me move it. I cannot connect. Yeah, it's blocking. But at the same time, observe what's happening here with this current. There's no current flowing through the circuit, and there's a reason for that. There's a reason why there's no current flowing through the circuit. Okay, see here the ammeter is measuring 0 current. The reason is that because this voltmeter here has a resistance that's very large. Okay, it has a resistance that's very large. If you want to build a voltmeter, you must have a voltmeter that has a very large resistance. Furthermore, do you see a measurement of -9 volts here? It's a -9 volts. Why is that? Because the negative probe of my voltmeter is connected to the positive tip of my battery. Okay. And similarly, the red probe of the multimeter, which is the positive end, is connected to the negative of the battery. If I want to see a positive measurement there, all you have to do is to invert the polarities here. Now I have +9 volts. Okay. So let's write that down. Okay. If we connect a voltmeter in series with a circuit, comma, the current goes to 0. Why is that? Why is that? It has to do with the intrinsic nature of a voltmeter. What do I mean by the intrinsic nature of a voltmeter? It has to do with the intrinsic resistance of every multimeter. Okay, all of them have a very high internal resistance. If you want to make measurement of voltage, you must build a voltmeter device that has a very large internal resistance. So because you have a very large internal resistance, so it's as though as you put a very large resistance between those 2 points, okay? It's having a voltmeter here is the same as having this circuit broke down right in here. The current is going to be 0. Why is that? Because the resistance between those 2 points is equal to infinity, the resistance of air, okay? Or the resistance of vacuum between, you have air between those 2 points, you know, you have a very large resistance between those 2 points. And same thing that you get here. You have a very large resistance between those 2 points. That's why you're getting a measurement of 0. So now let's see what happens if we connect my ammeter in parallel. Okay, students sometimes they do that. Yeah, students and professors too. Sometimes they do that by accident, right? And when you do that, you run the risk of damaging your ammeter. And I'm going to do that because this is a simulation. You know, this is a virtual device. I'm not going to damage any device here. I'm going to put my, you know what? I'm going to put my switch right in here, so I can have a better control of when the current flows or not. Okay, so here we go. Okay, here is my current flow in the circuit. And now I'm going to connect my amperimeter You don't do that in real life, okay? Otherwise, you can damage the device. Strictly speaking, you don't damage the device, you damage something else. You damage what we call the fuse, that protects the device. Fuses are very inexpensive devices that are capable of protecting very expensive devices. That's what fuses are. Right here, okay. I am connecting my, I'm not supposed to be doing that, remember? Ammeters can never be connected in parallel. And now I'm going to watch here the measurement, what's going to happen. There's no resistance here, right? In this circuit, there's no resistance whatsoever. The only resistance that you have is the internal resistance of the ammeter. I'm going to close it. Well, do you see what happens to the current? The current shot up, you know, and you can see a very high current here, 89,895 amperes. That's a very high current. Because this is a virtual device, it didn't break down yet. Okay? And it's written here, animation speed limit reached. Current animation speed reduced, right? To whatever percentage normal. Okay. Oh, look at my battery now. My battery is catching on fire. Okay, because I shorted my battery. Ammeter has very low internal resistances. Because the ammeter has very low internal resistance, when I connect the battery to a device like that that has a very low resistance, you produce a very high current. And the current may be so high that you can burn your battery or even break down your wire, okay? It has happened with me before, okay? I put a short circuit my battery. Instead of burning the battery, I burned my wire. My wire broke down. So let's open it and return everything to normal. And I'm going to write that down here. Okay, 1, if we connect the voltmeter in series of circuit, the current goes down to 0, Why is that? It has to do with the intrinsic resistance of every voltmeter. All of them have a very high internal resistance. Okay, the ideal voltmeter is the one that has an infinite value, an infinite resistance, okay? That's the ideal voltmeter. Now, what about ammeter? If we connect an ammeter, not in series, but in parallel with a circuit, with an element of a circuit, the current goes up to infinity. Okay, why is that? It has to do with the intrinsic resistance of every ammeter. All of them has a very low internal resistance. The ideal ammeter is the one that has a zero resistance. But in practice, the resistance can never be zero. In practice, the resistance is going to be very low. We can come up with a table here. Insert, what time is that? 11:54, right? Any questions about the lab? You know, it looks like we did most of it, right? So voltmeter, ammeter must be connected in parallel. Must be connected in series, okay? Internal resistance, very large, almost zero, very small, okay? Ideal internal resistance, When I mean very large, I mean very large compared to the resistance in the circuit that they are using. When I mean very small, it's very small compared to the resistance that you are using in the circuit. Ideal internal resistance, infinite. Here you go, 0. That's the ideal resistance of a voltmeter. Okay. And we can do the following. Let's see. Voltmeter connected, and I think we can connect it in parallel. Well, you have to know what happens whenever you connect the voltmeter in series, right? I don't think I can build a table for that. That's a good table here. Okay. Voltmeter in series. Okay, I guess we can stop right now. Do you have any questions? 4 minutes to 12 noon, right? Any questions about the lab today? Looks like most of you did everything that you're supposed to do, right? And also, don't forget to look at the corrections here, right? Most of the students already know how to look at that file that I put there in the folder. Some of you might not know. If you want to find that out, just stay around and I'll walk you through, okay? Any questions? Okay, so we can stop right now. I have office hours until 12:45. Okay. So I see you next week.
Professor,
Yeah.
for the Wiley homework, it's due on the 20th or at the end of the semester?
Let me see. Let me go there.
Because I know for last semester, it was at the end of the semester, and I think this time it says
Yeah.
the 20th.
Yeah, the semester I did differently. Okay, some of the homework I put a deadline there for, I don't know, March, but the other homework I made the deadline later on. Okay, so whatever deadline I put in there is the one that you see there. Okay, it goes
Okay. Sounds good.
7. Yeah, due March 31st. See that?
Okay.
Oh, this one I put due March 20. Huh? Okay, I'm gonna adjust this one. It's a good thing that you mentioned. I didn't notice that. But this one, I start to put that at the end of the course, right? Let me adjust the deadline of this one. Thank you very much for telling me that. I didn't know that I had on that. Edit. Okay, do. Let's put April, right? April 10. Well, I'll give a little bit more, right? April 10. You know what? Let's put March, the same date of the other one. March, what I put it? Just put 31st. Due date cannot be after lock date. What's the lock date? Let's see. Edit assignment settings. Okay, available from. Okay. So I'm gonna put March 31st, okay? And I'll put this one March 31st as well, since we already had the exam for this one, right? Okay, now we're in good shape. And let's go back to the assignment. Okay, yeah. See, this one I put there at the very end of the course. 31st, 31st. Okay. We have more time.
Thank you for the adjustment, Professor.
Okay, I hardly heard you. What did you say?
I said thank you for the adjustment, Professor.
Okay, thank you. Okay. Very nice of you. Thank you. Any more questions? Okay, I'll be here. I'll stop sharing my screen. And
Professor.
Yeah.
I had a quick question. I don't know if you ever got my email from a few days ago, but for our lab group, lab number 4, we had 3 people in our lab group, but I think one of them may have dropped the course. I'm not too sure, but right now in our lab group, it's only 2 of us. And I was gonna ask if there was any way we can maybe add one more person to our lab group, since I know all the lab groups have at least like 3 to 4 people.
yeah, if you do you know anyone that would like to join your group?
I don't really know anyone in the class, or like what group has 4 and not 3.
Yeah.
So I'm not really sure how to do it.
Yeah, there is group 1 has 4 students. Group 3 has 4 students. And all the remaining groups have 3. Okay. Yeah, I do see that your group has 2 students. That's right. It looks like someone dropped. Someone from your group dropped. So if you know any of those students on group 1 and 3, ask them if they want to join you. Okay, join your group. Group 1 and 3 has 4 students. All the remaining groups has 3. Okay, 2, 5, and 6 has 3. Ask the student of group, if you know any student in those groups 1 and 3, ask them if they would like to join your group. Okay, I cannot force them to join yours. Okay, but if you know someone in there that might want to join your group, that's fine with me. Okay, that'll be fine with me.
Okay, thank you.
Okay, thanks.